The modern data lakehouse was designed to solve a specific problem. Organizations wanted to combine the highly efficient economics of cloud object storage with the strict transactional integrity of a traditional data warehouse. Storage formats like Apache Iceberg and Delta Lake achieved this integrity. They introduced snapshot isolation, time travel, and schema evolution over open file formats like Parquet. But establishing this structure required a massive architectural compromise. To maintain the current state of a table, traditional lakehouses store their transactional metadata, the manifest lists, the snapshot histories, and the file pointers as deeply nested hierarchies of files right alongside the data inside the object storage. Object stores are optimized to hold raw bytes economically and durably. They are entirely unsuited for repeatedly resolving complex transactional relationships across thousands of small files. By forcing object storage to act as a relational engine, traditional architectures inherently cap their performance and inflate their query latency. Duck Lake is a framework that resolves this bottleneck by extracting the metadata out of the object storage entirely. Looking at this architectural diagram, we see the precise split. Large analytical datasets remain stored in open Parquet files on the cloud object storage layer. But all table definitions, snapshot histories, file references, and transactional records route into an indexed relational SQL database. Instead of traversing a fragile directory of files over a network to figure out which data is valid, Duck Lake resolves the table state by issuing an indexed SQL query. A heavy file traversal problem becomes a sub-millisecond database lookup. By moving the transaction state back into a native SQL database, Duck Lake accelerates query planning, reduces network overhead, and simplifies the entire management lifecycle of the lakehouse. A traditional write operation creates a tangled web of metadata. Inserting data triggers new Parquet files, manifests, and snapshots. Running a time travel query then incurs massive latency, forcing the engine to evaluate dozens of files over the network just to plan the query. Duck Lake replaces this traversal process using a relational metadata catalog. Executing a simple SQL where clause immediately identifies the correct snapshot. The catalog instantly prunes irrelevant files, mapping a direct line straight to the exact Parquet file required without unnecessary network lag. Returning to a relational database for metadata management restores a highly logical division of labor. Object stores hold the raw bytes, and databases manage the complex relationships. Modern lakehouse architectures rely on optimistic concurrency control. Multiple transactions can begin simultaneously, allowing readers to query data without being blocked by writers, assuming no overlapping changes will occur. If two write operations target the same table simultaneously, one succeeds while the other fails. System viability depends entirely on the cost of retrying that failed transaction. In a traditional file-centric lakehouse, a failed commit forces the losing transaction to expensively regenerate all metadata, rewrite manifest lists, and re-upload files over the network. This split-screen comparison isolates the operational difference. On the top, the traditional file-based retry is heavily bottlenecked by object store uploads. On the bottom, a Duck Lake transaction conflict is resolved by simply updating an indexed row in a relational SQL database. Relocating the transaction state to SQL keeps the conflict window incredibly tight, ensuring that when retries do occur, they are computationally weightless. High-frequency ingestion patterns, like IoT telemetry or microbatch operational logs, introduce one of the most persistent issues in data architecture, the small file problem. Writing continuous tiny batches of data results in thousands of minute Parquet files. This severely degrades read performance, wasting massive amounts of compute listing files, opening them, and evaluating fragmented statistics. Rather than relying entirely on heavy, continuous background compaction jobs to clean up the mess, Duck Lake prevents the issue at the source using a built-in mechanism called inlining. Small incoming inserts are intercepted. Instead of spawning tiny Parquet files, these microbatches are buffered directly inside the relational catalog as durable database rows. Once the rows hit a volume threshold, the system automatically flushes them out into a single, perfectly sized Parquet file. Inlining acts as an integrated buffer. It successfully bridges the gap between high-frequency operational streaming and highly optimized analytical storage. For over a decade, the data industry operated on the default assumption that any serious analytical workload required distributing the compute across multi-node clusters. That assumption created massive infrastructural footprints. Maintaining a traditional lakehouse requires balancing Spark clusters, managing Java virtual machines, debugging Hadoop libraries, and configuring external catalogs. Modern hardware renders much of this overhead unnecessary for standard workloads. A single machine equipped with fast local solid-state drives and high memory bandwidth can process immense analytical volumes locally. An embedded vectorized execution engine like DuckDB maximizes this hardware. Instead of reading every row, it relies on predicate pushdown to filter out irrelevant records at the storage level and selective scanning to read only the specific columns required for the query. Furthermore, local execution is not strictly limited by available RAM. For memory-intensive operations like massive sorts or hash joins, the engine utilizes a spill-to-disk mechanism, writing intermediate data directly to the SSD to maintain processing speed without failing. If we compare these architectural blueprints, the operational cost becomes obvious. Stripping away unnecessary distributed infrastructure removes dozens of failure points, reduces cloud spend, and eliminates specialized cluster maintenance, allowing engineering teams to spend their time actually building business logic. A relational catalog provides a structured environment that extends beyond tracking physical file locations. It functions as a machine-readable semantic layer, housing the context required for high-level analytical reasoning. Tables, views, and macros housed in the catalog carry embedded business context. Annotations can specify which team owns a dataset, what the fiscal rules are for revenue calculations, and exactly which quality thresholds must be met before reporting. Here, we see an AI agent plugging directly into that semantic context. By attaching to a standard SQL catalog, the agent can easily inspect relationships, infer schemas, map data ownership, and instantly generate an accurate analytical view pipeline. Attempting to build agentic analytics over traditional lakehouses yields high failure rates because the agents are forced to parse opaque object store APIs and navigate complicated distributed cluster configurations. A centralized SQL-native catalog is understandable, observable, and deterministic. That simplicity creates a highly reliable environment for human engineers and AI systems to operate within. The Duck Lake pipeline unifies high-frequency operational writes and long-term analytical storage. Operational events buffer as inline database rows, flush to compacted Parquet files, and are seamlessly queried through a local execution engine. The engineering goal is not to adopt the most complex technology available. The goal is to use the absolute simplest technology that reliably solves the problem and can be actively supported by the organization. This pipeline flowchart illustrates a highly pragmatic approach to modern data architecture. Store the analytical data in open files, manage the metadata relationships with SQL, execute queries as close to the data as possible, and introduce distributed complexity only when the specific workload proves it is necessary.